Well, this lecture is about the AC measurements, where we will discuss about the instruments which are capable of measuring the AC current, voltage, power, and we will also discuss the frequency meter. This presentation scheme of this lecture, it includes the AC instruments, the basic discussion about it. Then we will be discussing the electrodynamometer and the rectifier type of instruments. This will be followed by the wattmeter, which is capable of measuring the power, and finally, we will discuss the digital frequency meter. Well, in the earlier lecture, we had discussed about the DC measurements, where we had used the PMMC type of meter or the d-Arsonval movement, where we find that whenever a current is passed through a coil which is suspended in the permanent magnetic field, then a torque is experienced by the coil and the coil begins to deflect, and hence the pointer. But those types of meters cannot be used for measuring the AC, because AC is varying signal which continuously varies with time, having the positive and the negative halves. If that meter is used for measuring the AC, then during the positive half the pointer will be deflected in one direction, and in the negative signal or the negative half the pointer will be deflected in the other direction. And if it is a high frequency signal, then due to the high inertia of the coil, the pointer will get stuck at a particular point and the pointer will then read 0. So, as such we cannot use the PMMC meter in measuring the AC. So, we slightly modify the PMMC meter by removing the permanent magnet, and we use the coils such that the measuring current itself produces the magnetic field, instead of the case when the magnetic field was being produced by the permanent magnets. So, as far as measurement of AC is concerned, we use two types of meters. It is the electrodynamometer, and secondly it is the rectifier type of instruments. Now, both these instruments or both these meters, they are based on the PMMC type of movements only, but here as said earlier, we will not be using the permanent magnet. Instead, we will be generating the magnetic field which will be depending on the current to be measured. So, coming on to the electrodynamometer, it is a accurate AC voltmeter or ammeter, not only at the power line frequencies, but also at the lower audio frequencies. So, electrodynamometer is an efficient instrument to measure the AC. Here we find that there are two coils which are the fixed coils, and there is a moving coil which is fixed in the magnetic field produced by the two fixed coils. Now, if we see it carefully, we find that all the three coils basically they are in series with each other. The wire extends up to coil 1 fixed coil, then up to coil 2 which is again a fixed coil, and the wire of this coil extends to the moving coil which is between the coil 1 and the coil 2. Since the current is passing through the coil 1 and coil 2, therefore, the magnetic field B is produced between these two coils, and this magnetic field is proportional to the current which is being passed through these coils. Simultaneously, the same current is also flowing through the movable coil. So, due to this, as there is a presence of magnetic field and this moving coil experiences a torque which is given as tau equal to B I A N, B being the magnetic field which is due to the current flowing through the coils 1 and 2, I is the current itself which is to be measured, A is the area of cross section of the moving coil, and N is the number of turns in the moving coil. As a result of this torque, the pointer deflects. Now, coming back on to the generation of the magnetic field, here we find that this magnetic field is itself due to the current which is to be measured. So, we say that higher the value of current, higher will be the magnetic field. So, the magnetic field B here is directly proportional to the current I. Now, if the value of this B proportional to I or B equal to K I, K being a constant, if the value of this B is fed into this original equation tau equal to B I A n, we find that tau is proportional to I square, A and n being the constant value. So, we find that the deflection in the pointer is due to the torque, and here the torque is proportional to the square of the current, and we can say that the deflection obtained in the pointer is proportional to the square of the current. So, under this condition we say that the pointer is showing the square of the current. Now, since we are measuring the AC, therefore, due to the variations in this AC signal, the pointer will deflect to and fro, and at high frequencies we say that since the signal is varying, so the pointer will also deflect and it will become static at higher frequencies at a particular point, and this point can be said to be the average of the signal. So, right now the pointer is showing the square of the current value which is averaged at a position, and this averaging has been done because of the inertia of the coil. So, we can say that the pointer is reading the average square value. We know that the AC is measured as the RMS value, root mean square value. So, currently the pointer is reading the mean square value. Now, in order to obtain the root mean square value, the scale is calibrated in terms of the root. So, we obtain the root mean square value through the pointer, again saying that although the pointer is indicating the mean square value, but the scale has been calibrated as the root. So, we obtain the root mean square value. So, this electrodynamometer shows the RMS value of the measured AC. Now, considering the disadvantages of the electrodynamometer, we say that it consumes high amount of power, which is the direct result of its construction. This is because that the power consumption is higher, because the same current which is to be measured is itself producing the magnetic field. So, the magnetic field should be strong enough to produce a deflection. So, we say that the electrodynamometer consumes higher power. Moreover, the sensitivity of the electrodynamometer is very low, and as we say that the coils have been used through which the unknown current is flowing through it. So, the reactance of the coils also increases at the higher frequencies, XL being equal to 2 pi FL. So, at higher frequency the reactance of the coil, that is XL, will be higher. So, all these are the disadvantages of the electrodynamometer. So, coming on to the next type of instrument, that is the rectifier type of instrument. Here we use the PMMC directly as it is. What we do is that the AC to be measured is first fed to a rectifier. The rectifier converts this AC into DC, and this DC is then measured by the PMMC or the d'Arsonval meter, and later this whatever has been read by the PMMC meter is then calibrated in terms of the RMS value. So, here we use the rectifier. So, it is called the rectifier type instrument. we know that the rectifying element is the diode. It may be a germanium or a silicon diode. We generally use the bridge rectifier because of its obvious causes. The bridge rectifier produces a pulsating unidirectional current through the meter, and this meter movement over the complete cycle of the input voltage, the pointer moves. Now, there is a factor we define as the form factor, which is given as the ratio of the effective value of AC and the average value of AC. Average value of AC is almost the DC which has been measured by the PMMC meter. So, by multiplying the form factor with the DC value that has been read by the meter, we obtain the effective value of AC. Now, this form factor is a constant value. For example, for bridge rectifier, the form factor comes out to be 1.11, and so by multiplying the value of DC which has been read by the meter by 1.11, we obtain the effective value of AC. So, this is the rectifier type of instrument, where we first rectify the AC which is to be measured, and then it is measured by the PMMC meter in the form of DC, and then we can convert that DC into the effective value of AC by multiplying it by the form factor, or accordingly we can calibrate the scale itself. Now, coming on to the watt meter, as the name suggests, watt meter, it is capable of measuring the power, both AC and DC power can be measured. Here the fixed coils or the field coils are connected in series and carry the total line current AC, the line current AC which is the current from the input, from the signal which is whose power is to be measured. The movable coil is located in the magnetic field of the fixed coil, is connected in series with the current limiting resistance across the power line and carries a small current IP. Here there are two coils, fixed coils through which the current is being passed, IC is being passed, and there is a movable coil through which the current IP is being passed. So, whenever the current is passed through this arrangement, again due to the d orthogonal movement, the pointer will deflect, and this time the deflection can be given as theta average is equal to k upon t integral 0 to t IC IP dt. In the previous case, when we were talking of the electrodynamometer, the deflection was proportional to I square, because the current flowing through the fixed coils and through the movable coil was same, since they were in series. But since there is a node occurring between the connection of the fixed coil and the movable coil, so the current through the fixed coils, as said earlier, is IC, and the current through the movable coil is IP. So, instead of getting I square over here, we are getting IC into IP. So, the deflection is proportional to the integral of IC IP, and this equation can be modified as the deflection is proportional to the product of E and I, E being the voltage of the input signal and I being the current from the input signal. So, the product of E and I will give us the power. We say that by definition that average power is given as 1 upon T. Average power means the power in a cycle, it is 1 upon T integral 0 to T E I dt. So, we find that the average power is indicated by the deflection in the pointer, which indicates that the electrodynamometer movement connected in this configuration has a deflection proportional to the average power. Now, coming on to the digital frequency meter, as the name suggests that this circuit is capable of measuring the frequency of the input AC signal, and obviously the circuit is of digital nature. So, the frequency counter, it operates on the principle of gating action. That is, the input signal is converted into pulses of similar frequency, and these pulses are passed through a gate, that is said to be the gating action. This pulses are passed through the gate for a particular period of time, and these pulses are then counted by the counter. If the gate is opened for 1 second, we suppose, and the count in the counter is 10, then we say that 10 pulses has been counted by the counter in 1 second. So, it gives a frequency of 10 hertz, that, and since the frequency of the pulses has been obtained from the input signal frequency. So, the frequency of these pulses is similar to the input signal. So, this is the block diagram of the frequency meter. The input signal is first fed to a input signal processor. Now, this signal processor, it may be an amplifier in case if the input signal is a weak signal. It may be a attenuator in order to attenuate the signal if required, and moreover this input signal is also converted into a pulses through this signal processor. For example, it may be a Schmitt trigger which converts the input signal or the sine wave into the pulses, and the pulses obtained at the output of the signal processor will have the frequency similar to the input signal. So, basically this input signal processor, it may amplify the signal, it may attenuate the signal, and moreover in addition to this, it converts the input signal into pulses. Now, followed by the input signal processor is the AND gate, as can be seen. The another input to the AND gate is from the time base. This time base generates the pulses, and the width of the pulse can be controlled through this time base. So, if we say that the time base generates a pulse, let this pulse be of 1 second. So, that is, this pulse remains at high state or at 1 for 1 second, then all those pulses which are coming from the input signal processor will pass through the gate, and after the end of 1 second the gate will close. The pulses reaching the output of the AND gate will be counted by the decade counter, and we say that the decade counter contains the count of the number of pulses which are appearing in 1 second, or in other words, the counter contains the frequency of the pulses, or in other words, the counter contains the frequency of the input signal, because the frequency of the input signal is equal to the frequency of the pulse being obtained at the output of the signal processor, and hence at the output of the AND gate. So, we say that this is the frequency which has been measured in hertz, because the time period of the pulse that has been produced by the time base is 1 second. Now, in case if we say that the time base produces a pulse at the input of the AND gate of say 1 millisecond, then at the output of this AND gate we will obtain the count in the counter in the units of kilohertz, because we will be obtaining the count as the number of pulses reaching the counter in 1 millisecond. So, the number of pulses in 1 millisecond will turn up into the units of kilohertz. Similarly, if the time base produces pulse of 1 microsecond, then obviously the counter will read the frequency in the units of megahertz. So, this count in the counter is then passed to the memory through the strobe signal, which is again generated by the time base. So, as soon as the time base signal or the time base pulse generated by the time base block goes low, then this time base also generates the strobe signal, and which is fed to the memory, and when this strobe signal is fed to the memory, the count in the counter is loaded into the memory and is displayed onto the display. Now, again before the beginning of the next measurement cycle, the time base also generates a reset signal, because before the beginning of the next measurement cycle the counter should be reset to 0, and but at the same time, since the memory is having the previous count stored in it. So, the display will remain stable unless the next strobe signal is generated after the next measurement cycle. Now, as can be seen in this timing diagram, the same has been explained that when as long as the time base signal is 1, then the input pulses reaches the output of the gate and are accordingly counted. So, that is how the frequency meter works. So, here the heart of this frequency meter is the decade counter. As we know that basically it is a digital counter which comprises of a number of flip flops, basically the JK flip flops, which are connected such that the output of each JK flip flop acts as the clock input to the next JK flip flop, and obviously all the JK flip flops are in toggle mode. So, as the pulse arrives at the clock input of the first JK flip flop, then the output of this first JK flip flop toggles, and this toggle effect, it acts as the clock input to the next JK flip flop, and the output of the next JK flip flop toggles. This process continues, and if we are using suppose n JK flip flops are connected such that the output of one JK flip flop acts as the clock input to the next JK flip flop. If there are such n JK flip flops, then the counter is capable of counting from 0 to 2 to the power n minus 1, that is suppose the number of JK flip flops are 3, then it is capable of counting from 0 to 2 to the power 3, that is 8 minus 1 equal to 7. So, this is how the counter works, but here we have used the decade counters. Decade counter means which is capable of counting from 0 to 9, and a number of such 0 to 9 decade counters have been synchronized with each other. And in this type of counter, suppose we are using 4 JK flip flops, then it will be able to count from 0 to 2 to the power 4, that is 16 minus 1, that is 15. But if we are designing a decade counter, we want to count from 0 to 9, that is 10 states are to be counted. So, we generate a logic such that the each JK flip flop is cleared when the count reaches 10 in binary, that is 1 0 1 0. So, each JK flip flop has been cleared. So, again the count becomes 0. So, this is one decade counter which can count from 0 to 9, and at ones place, tens place, hundreds place, thousands place, we are using such type of decade counters. When the decade counter of ones place reaches 9, then it generates a pulse to the next decade counter which is at the tens position, and it gets incremented by 1. So, this type of counting continues. Now, when this decade counter at tens place it reaches 1 to 9. So, it again generates a signal such that the decade counter at hundreds place it gets incremented by 1. So, this process continues, and a series of such decade counters results into a counter which can count in thousands or lakhs, whatever it is. So, in this lecture we have discussed about the AC measuring instruments, where we have discussed majorly two type of instruments. One is the electrodynamometer and the rectifier type of instrument. The electrodynamometer, it is almost similar to the PMMC meter, except one difference, that here we are not using a permanent magnet. Instead, we are generating the magnetic field by the current which is to be measured. So, this current is made to pass through two fixed coils, and when the current passes through these two fixed coils, a magnetic flux is generated between them, and the movable coil as was in the case of PMMC. It is similar to that only, where the movable coil is suspended between the magnetic field. The only difference is that the magnetic field here is not due to the permanent magnets, it is due to the current which is flowing through the two fixed coils, and remember that this current is the same which is to be measured. As a result of this, we obtain the deflection in the pointer which is proportional to the square of the current, and because of the varying signal, the pointer also varies. It moves here and there, it moves to and fro, and it gets steady at a particular position due to the inertia whenever a high frequency signal is fed to it. And in order to obtain the root mean square value, we calibrate the scale in terms of root. And then we had discussed the disadvantages of the electrodynamometer, where we say that it consumes high power, its sensitivity is low, and the reactance of the coils varies due to the variation in the frequency of the input AC signal. So, then we discussed the rectifier type of instruments, where we use the PMMC meter itself. So, in order to use the PMMC, we first use the rectifier circuit, which converts the input AC into DC, and this DC is directly measured by the PMMC meter. Later on, either the scale is calibrated in terms of the RMS value using the form factor, or it can be directly multiplied by the form factor to obtain the effective value of AC. Followed by this was the wattmeter, where we had discussed how the wattmeter measures the power, and then we had discussed the digital frequency meter, where the input signal is converted into pulses and is passed through the gate, which remains open for a particular period of time, and these pulses, when passes through the gate, are counted by the counter, and this counter hence represents the count of the pulses which has been obtained in a particular time period, and hence it can be converted into the frequency. If the time period of the gate for which it remains active is 1 second, then the counter has the count which indicates the frequency itself, and this is then transferred to the memory and hence the display, and that is how the frequency meter works, the digital frequency meter works, and that is all, and you might have enjoyed the lecture. Thank you.